What's up, everybody? We have a circuit problem today. This is what's referred to as a QQT problem, qualitative quantitative translation problem. You should expect one of these on this year's AP test. So we have a circuit problem. The key idea here is that we have a variable resistor here, and we're essentially going to analyze this. We have two students making statements, and there we go. So the first thing we're going to do is go ahead and look at the two student statements, and they want us to graph it out. So student 1 says the current starts at non-zero value and decreases. So we're going to have our current somewhere over here to non-zero value. We are going to decrease it as an asymptotic curve, right? So that means some non-value, non-zero value. So we're starting here at some current I, and we're going to decrease it to some other current I that's non-zero, and we want it to be asymptotic with that. So let's go ahead and draw this in. It should curve down since it's an asymptote. We want it to kind of approach that point, never quite reach it. And this is student 1. We'll go ahead and label that student 1. Student 2 says it's just going to start at non-zero as well, and it is going to decrease linearly towards 0. So this one seems pretty easy, it's pretty straightforward. We'll start at non-zero, and we'll just go ahead and decrease that as a line to 0. And we'll label that as student 2. Question B says we want to derive the equation between I, showing I, and the variable resistor. So if we look at our circuit, notice I, this is the total current going through the circuit. So in other words, if we could reduce this circuit to a single R equivalent resistor, then we could easily find that I here, right? We'll just use Ohm's law, so we'd have essentially I equal to V over R, so epsilon divided by, and I'll write this as REQ. And then it's just a matter of solving for REQ. So what we'd want to do is see that these two are in series. So this should be just the sum, right? R2 plus RV. And then we have R1 in parallel with that combination. So REQ, let's write this out. REQ, actually 1 over REQ, right, should be equal to 1 over R1 plus 1 over R2 plus RV. Alright, then we just want to sub this in. Actually, what I would do is just kind of, if you notice, this is essentially epsilon times 1 over REQ. And so instead of, doing some crazy algebra here, I'll just sub in for 1 over REQ over here. In other words, my equation I, let's draw this over here, I should equal epsilon times the quantity 1 over R1 plus 1 over R2, 1 over the whole thing, R2 plus RV. I think that's fine to leave it like this. You can take a look in the solution manual, and they kind of do a little bit more algebra, but honestly, I think this is fine. Question C is looking at us to analyze for a case when RV equals 0. So the first question says, is this consistent that the current starts at a non-zero value? So in other words, when RV equals 0, is the current going to be non-zero? So this is fairly straightforward. Once you have your equation, when RV equals 0, this goes to 0, right? And so your equation essentially becomes I equals epsilon times 1 over R1 plus 1 over R2. And so yes, I mean, I would just say something like yes, okay, and then probably do this substitution, show that that it can't be 0, right? So no matter what, I is non-zero for any value of R1 and R2. Okay, I guess the only way really you could have I to be 0 is if you had no voltage, right? If epsilon was 0, if this was 0, then that's the only possible way you could have I to be 0. The second part of this question is asking, is it consistent with our circuit diagram? And the answer definitely would be yes. I mean, notice our circuit's going to essentially become this. If RV equals 0, you have a simple parallel circuit, right? And so you can see that no matter what, current flows in all branches. In all branches, or the whole circuit. And no matter what, you will have a non-zero current. So the last part of the question is asking, what about when RV is very large? Okay, so we'll just evaluate this, and they want to know, does this apply to either student? So RV large, essentially when RV gets really big, if you look, the 1 over R2 plus RV, if RV gets large, let's say it approaches infinity, that means this term is going to approach 0, right? So in other words, I will essentially equal epsilon over R1. So which student does that apply to? Remember, student 2 said this would be 0, S2 said this would equal 0, and S1 said it would be basically non-zero, right? So greater than 0. And you can see this is definitely applies to student 1. So again, you'd want to say something like, well, student 2 said it would be 0. You derive this equation here, and you can see that it's not 0. And student 1, it is greater than 0. You could also, I suppose, if you notice, E over R1 is less than, what do we have before? E over R1 plus E over R1, R2 plus RV. So you could also say, well, that's clearly less than that, because remember, part of that student statement was saying that it decreases, right? It decreased, it started up larger, and it decreased to some smaller value, and we're confirming that as well. So the very last question, is this consistent with our circuit diagram? Yeah, I think so. If you notice, as this gets large, as this like approaches infinity, then essentially this whole branch here is going to be super large, right? Essentially infinity. So all current in this situation is currents coming through. All current's going to continue to flow just through R1, and this one would be like really, really small, okay? Approximately 0 is what that value would be. So yeah, I would just talk about that. Essentially, this circuit becomes a single resistor circuit. So this would be our new circuit for RV large. I'm just going to say approaching infinity. And so all the current, so current still flows. Remember, that's the key idea. Current flows only through R1. So it's not going to be 0, but it's only going to flow through R1, and there'll be 0 through that other branch. All right, hope that helps. Let me know if you have any questions.